Hello there and welcome back to the Science Sleepy Mind. Picture this. It is a Tuesday morning in Cambridge, England. The kind of Tuesday that doesn't announce itself. The milk in the lab fridge is almost certainly past its best before date. Someone has left an unwashed mug in the sink again with what appears to be a philosophical commitment to leaving it there forever. A kettle is boiling somewhere down the hall. And then, quietly, without ceremony or trumpets or any of the dramatic lighting that this moment absolutely deserved, a set of data appears on a computer monitor in a university office. Numbers, graphs, peaks and valleys on a spectral readout. The kind of thing that most human beings would glance at for 2 seconds and then go find the biscuit tin. But the people in this room are not most human beings. They are some of the most careful, controlled, deliberately undramatic scientists on Earth. And one of them pushes their chair back from the desk, presses both hands flat on the surface, and goes very quiet. Because inside those peaks, inside what looks, to the uninitiated, like a mildly interesting line graph, is a message. A chemical message, written in the wavelength of starlight that travelled 120 light-years across the cold, empty silence of space before filtering through the atmosphere of an alien world and landing, photon by patient photon, in the golden mirror of the most extraordinary machine humanity has ever built. And the message, decoded with the precision of modern astrophysics, spells out a molecule, a specific molecule, one that, on Earth, is produced almost exclusively by one thing: life. You feel that right now in whatever corner of the world you've wrapped yourself in tonight. That small electric prickle at the back of your neck that arrives when something is genuinely, historically enormous. Because this is not a small story. This is not a footnote or a scientific curiosity or a headline that will be forgotten by Thursday. The James Webb Space Telescope, humanity's largest, most powerful, most expensive eye in the sky, looked at a planet 120 light-years away and detected what appears to be a chemical signature that, on every planet we have ever studied, is produced almost entirely by living organisms. And scientists have attached a confidence level to this finding of 99.7%. That is 3 nines, a decimal, a 7, and a percent sign that has been quietly detonating in the astrophysics community ever since. Now, before you pull that blanket up to your chin and let gravity do its work on your eyelids, let's be completely honest about one small detail. If life does exist on K218b, which is what this planet is called, and if that life has even a fraction of the territorial instinct, the competitive drive, and the enthusiastic aggression that Earth life has demonstrated over 4 billion years, then your personal survival odds upon first contact are something we should probably workshop before committing to any decisions. You probably won't survive this one, friend. Sweet dreams, though. So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And while you're still alert enough to type, drop a comment below. Tell me where in the world you are right now and what the clock on your wall says. There is something quietly wonderful about knowing that someone in a rain-soaked apartment in Seoul, and someone under a ceiling fan in Nairobi, and someone in a suburb of Buenos Aires who has absolutely told themselves, just 10 more minutes, approximately 4 times tonight, are all here, falling asleep to the same question. Are we alone? Tell me where you're listening from. I like knowing who's out there. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. In September 2023, a paper appeared in the astrophysical journal Letters, authored by Niku Madhusudan and a team of researchers at the University of Cambridge. The paper described what the James Webb Space Telescope had detected in the atmosphere of K218b. Carbon dioxide, methane, and, most explosively, possible traces of dimethyl sulfide, a molecule that on Earth is produced in significant quantities primarily by marine microorganisms. The paper was measured and careful, written in the precise hedged language that serious science demands. It did not say, "We found aliens." It said, in the quiet vocabulary of academia, that they had detected a chemical fingerprint consistent with biological activity. The distinction matters, but the implication was clear to anyone reading between the methodologically rigorous lines. The internet, predictably, heard "we found aliens" and ran with it at full speed across a motorway. Headlines erupted in 17 languages within hours. Social media users who'd been arguing about things of substantially less cosmic significance stopped mid-argument to look upward. Scientists across 6 continents began making coffee at 2 a.m. and texting colleagues they hadn't spoken to in years. Here is your mainstream historical anchor for the evening. This is not the first time humanity has stood at the edge of this announcement. In 1896, the astronomer Percival Lowell, a wealthy, enthusiastic, and magnificently overconfident Boston aristocrat, published a book arguing that he had spotted a network of artificial canals on Mars through his telescope. He proposed a dying Martian civilization, engineers of planetary waterworks, beings clever enough to move water from polar caps to dry equatorial regions. He was wrong. There were no canals. Scholars still debate whether what Lowell observed was atmospheric distortion, the limitations of 19th century optics, or simply the human brain's remarkable, well-documented tendency to find meaningful patterns in visual noise, a phenomenon called pareidolia. The debate remains, in academic terms, genuinely open, but is passion seeded something permanent, the public's longing for the answer to the oldest question in the night sky? Here's your quirky tidbit for this first section. Dimethyl sulfide, the molecule at the centre of tonight's entire story, is the chemical responsible for that specific smell you associate with the ocean, that salty, seaweedy, alive and complex perfume that hits you the moment you crest a coastal hill and the sea appears below. It is produced by marine plankton and bacteria in vast quantities, diffuses into the air, and gives Earth's coastlines their distinctive olfactory personality. If the Webb detection is correct, K218b currently smells faintly of a summer morning at the seaside. Something 120 light-years away smells of the beach, and something out there might be alive enough to make it smell that way. You settle a little deeper. The ceiling is dark. Above it, beyond it, past the atmosphere and the moon and every human-made object except one brilliant golden machine, there may be a world where something small and ancient and alive is doing what life does, eating, breathing, dividing, persisting. Tonight, you will learn exactly what that world is, what we found there, and what it would mean if what we found turns out to be true. Let's begin. The James Webb Space Telescope is, by almost any meaningful measure, the most complex object humanity has ever successfully deployed in space. This is not marketing language or scientific pride talking. This is the sober, slightly shell-shocked assessment of the engineers, physicists and project managers who spent roughly 25 years of their lives conceiving, designing, building, breaking, redesigning, and eventually launching this machine into the void. People gave careers to this telescope. Marriages were tested by it. Sleep schedules were genuinely sacrificed. And when it finally worked, when it exceeded its design specifications within weeks of becoming operational, those people cried, not metaphorically, but with actual physiological tears, in mission control, in front of cameras, without apparent embarrassment. It had earned those tears. You're going to understand this machine tonight, not in the way its engineers understand it. You will leave the thermal modelling and the wavefront sensing algorithms to people whose hobbies include quantum mechanics, but in the way that makes the K218b data feel real, feel earned, feel like the result of something that humanity chose, deliberately and at great expense and difficulty, to build together. Start with the mirror. Webb's primary mirror spans 6.5 meters across, roughly the width of a city bus standing on its end, assembled from 18 individual hexagonal segments arranged into a single honeycomb surface. Each segment is made of beryllium, a metal chosen for its extraordinary stiffness relative to its mass. Because when you're trying to align a reflecting surface to nanometer precision in the cold vacuum of space using small motorized actuators, you need a material that behaves predictably and doesn't deform under temperature changes. Each segment is coated with a layer of gold, not for aesthetics, though the photographs are spectacular, but because gold is an exceptionally efficient reflector of infrared light, which is the part of the electromagnetic spectrum Webb is designed to see. Why infrared? Because the universe has a filing system, and the most interesting things are often filed under infrared. Distant galaxies, their light stretched by the expansion of the universe into longer and longer wavelengths, glow most brightly in infrared. Stars forming inside dusty nebulae, invisible to optical telescopes because the dust absorbs their light, can be seen in infrared because their warmth penetrates the clouds. And the atmospheric chemistry of distant planets, the chemical fingerprints of molecules that absorb specific wavelengths of filtered starlight, includes many crucial signatures in the near and mid-infrared range. To read those fingerprints, you need a telescope designed for this part of the spectrum. Your mainstream historical fact for this section: the telescope is named after James E. Webb, who served as NASA's administrator from 1961 to 1968 and oversaw the Apollo program. His tenure was considered a model of effective scientific management. He balanced human spaceflight ambitions with substantial investment in robotic science missions and university research. The naming became modestly controversial in later years, when historians began examining a 1950s federal policy under which gay employees were systematically dismissed from government service. Scholars still debate the extent of Webb's awareness of and complicity in this policy. Some argue he was a passive administrator implementing existing rules without particular enthusiasm. Others suggest he had more direct involvement. The debate is genuine and ongoing, and represents one of those moments where history insists on being complicated rather than clean. Webb launched on Christmas Day, 2021, at 7:20 in the morning local time, from the Guiana Space Center in Kourou, French Guiana, aboard an Ariane 5 rocket. The launch window was a Christmas gift nobody had asked for, but everyone desperately wanted. People watched from home, from laboratories, from science classrooms, from YouTube on their phones in various states of hungover Christmas morning. Mission control was quiet in the specific way that comes from knowing that everything done for 25 years was either about to matter or not. The journey to its operating position took approximately 30 days and involved one of the most nail-biting mechanical deployments in the history of space exploration. Webb had to fold up like a piece of complicated origami to fit inside the rocket fairing. The mirror sections folded in, the secondary mirror folded in, and most critically, the sunshield packed down into a small fraction of its operational size. Unfolding all of this in the right sequence in the cold vacuum of space, 1,000,000 miles from any possible repair crew, required 344 separate single-point mechanisms, 344 individual latches, hinges, pulleys and actuators, each of which had to work correctly. If anyone failed, the mission was in serious trouble. All 344 worked. The lead project scientist later described watching the sunshield deploy as feeling like watching someone attempt to fold a tennis court-sized piece of origami in space from 1,000,000 miles away, with no ability to intervene. A reasonable description of what was effectively an extremely expensive, extremely fragile act of faith. The sunshield, 5 layers of a material called Captain, each layer thinner than a human hair, now separates Webb's instruments from sunlight with such efficiency that the temperature difference between the sun-facing side and the instrument side is around 300 degrees Celsius. The telescope's mirrors and detectors sit at around -233 degrees Celsius, just 40 degrees above absolute zero. This is essential. Webb is looking for faint heat signals. If the telescope itself were warm, its own thermal emission would drown out the delicate infrared light it's trying to detect, like trying to hear a whisper while standing inside a jet engine. It has to be cold, nearly as cold as space itself. Your quirky tidbit. The gold coating on each of Webb's mirror segments is applied in a layer exactly 100 nanometers thick. 100 nanometers is approximately 1,000th the width of a human hair. If you applied the same thickness of gold to every surface in a typical bedroom, the total gold used would weigh less than a 1-pound coin. Space engineering operates at scales that refuse to be intuitive, no matter how many times you encounter them. Webb reached its destination, the second Sun-Earth Lagrange point, Vel 2, 1.5 million kilometers from Earth in the direction away from the Sun, and settled into a halo orbit there. L2 is a point of gravitational balance where the combined pull of the Sun and Earth allows a spacecraft to orbit while remaining roughly fixed relative to Earth. It is far enough from Earth that no human crew could ever visit for repairs, but stable enough to remain indefinitely with occasional small course corrections. Webb will observe from there for at least 20 years, possibly more. Every data set it produces, including the K2-18b atmospheric analysis, has been earned by 2.5 decades of engineering, $10 billion of investment, and 344 perfectly executing mechanisms in the dark of space. That data was worth all of it, and K2-18b was waiting for exactly this level of precision. The planet was not supposed to be the one. In the world of exoplanet science, celebrity has a hierarchy. There are worlds that attract attention, funding, conference keynotes, and the kind of nervous excitement that causes astronomers to check email at 3 in the morning. For much of the 2000s, that celebrity hierarchy was dominated by the TRAPPIST-1 system, a family of 7 Earth-sized planets orbiting a red dwarf star about 40 light-years away, at least 3 of which sit in the habitable zone. TRAPPIST-1 planets have names, essentially. They are designated TRAPPIST-1b through TRAPPIST-1h, and they have fan followings in the exoplanet community that border on the affectionate. K218b, by contrast, spent most of its early scientific life on the second shelf, behind the headline acts, listed in catalogues without drama. It was found in 2015 by the Kepler Space Telescope during what astronomers called the K2 mission, the second phase of Kepler's operational life, after the failure of 2 of the spacecraft's reaction wheels forced scientists to redesign the mission to use solar pressure for stability. It was a clever engineering workaround that gave the telescope a new lease on life and a new swath of sky to survey. K218b was discovered the way the overwhelming majority of exoplanets are discovered, by transit detection. Kepler watched the light from thousands of stars simultaneously and flagged the ones that dimmed periodically in the regular pattern that indicates a planet passing across the face of the star. For K218b, the dimming was tiny, less than 1% of the star's total light, but Kepler was built to see exactly this. It flagged K218b, and follow-up analysis confirmed a real planet. Initial characterization placed K218b in a category called sub-Neptune, or mini-Neptune, a class of planet with no representative in our own solar system. Our solar system makes an abrupt jump in size from Earth, the largest rocky planet, to Neptune, the smallest ice giant, with a factor of roughly 4 in radius and 57 in mass separating them. The galaxy is full of planets in that gap, worlds larger than Earth but smaller than Neptune, whose internal compositions are disputed and whose surface conditions range from possibly habitable to definitively catastrophic, depending on assumptions that are still being refined. K218b, with a mass of about 8.6 times Earth's and a radius about 2.6 times larger, sat squarely in this contested middle ground. Your mainstream historical fact: the Kepler Space Telescope, which found K218b, was launched in March 2009 and retired in October 2018 when it exhausted its fuel supply, unable to continue pointing precisely. In just under 10 years, it confirmed the existence of more than 2,600 exoplanets and flagged thousands of additional candidates. Before Kepler, we knew of only a few hundred exoplanets, most found by other methods. After Kepler, the number of known exoplanets has exceeded 5,000, with estimates suggesting the Milky Way contains hundreds of billions of planets. That is, roughly 1 planet per star on average, and possibly more. This single shift in our understanding of cosmic real estate is one of the more quietly staggering things the 21st century has contributed to human knowledge. K218b orbits a red dwarf star designated K218, located approximately 120 light-years from Earth in the direction of the constellation Leo. It completes 1 orbit every 33 Earth days, which sounds brisk but makes perfect sense for a planet in the habitable zone of a dim red dwarf. The habitable zone of such a cool star sits much closer in than Earth's distance from our warm yellow sun. At this orbital distance, the amount of starlight K218b receives is comparable to what Earth receives from the Sun, placing it at least in terms of energy budget, within the theoretical range where liquid water could exist on its surface. When something sits in the habitable zone of its star, astronomers take notice. The phrase habitable zone doesn't mean a planet is habitable. It means the orbital distance is consistent with liquid water under certain atmospheric conditions. Mars is in our Sun's habitable zone. Mars is not, as of our most recent extensive investigations, teeming with life. But the habitable zone placement is the first filter, the first worth looking at more carefully, and K218b passed it. The first real moment of scientific excitement about K218b came in 2019, and it came from Webb's predecessor, the venerable Hubble Space Telescope. Two independent research teams, working with the same Hubble dataset but unaware of each other's analysis, completed their work at nearly the same time, and both announced the detection of water vapour in K218b's atmosphere. The announcement arrived within days of itself in published form, and the story of two teams racing toward the same finish line carries a very human comedy. Picture the panicked email inboxes when pre-publication manuscripts started circulating. Scientists still debate which team technically scooped the other, but both papers were published, and both received credit. Water vapour in the atmosphere of a potentially habitable exoplanet, the first such detection in history. Not water, not an ocean, water vapour, but it was enough. K218b went from interesting data point in a catalogue to planet we should watch very carefully. And astrophysicists began lobbying for James Webb Telescope time to study it properly. Your quirky tidbit: K218b's orbital period of 33 days means that in a single Earth year, the planet completes approximately 11 full trips around its star. Children on K2-18b, were there children? Were there a concept of children? Were there a concept of birthdays, which is already asking a lot from marine microorganisms? Would accumulate 11 years of age before an Earth child finished its first. The candles on the birthday cake situation would escalate rapidly. Balloon vendors would be doing well, financially speaking. The team at Cambridge, led by Niku Madhusudhan, had been developing a theoretical framework for a new category of planet they were tentatively calling Hycean worlds. K218b fit the profile. The size was right. The temperature range was in the right zone. The atmospheric hints from Hubble pointed in the right direction. When Webb came online, K218b was near the top of Madhusudhan's observation wish list. He wanted to look at this planet the way a doctor looks at an X-ray, not with a guess about what's there, but with a tool capable of actually showing it. What Webb showed him changed the conversation in ways the field is still processing. The word Hycean is not in any standard dictionary, not yet. It was coined in 2021 by Niku Madhusudhan and colleagues, a portmanteau of two words, hydrogen and ocean, designed to name something that existing planetary science didn't have a tidy shelf for. Before the Hycean framework was proposed, the mini-Neptune category that K218b sat in was treated somewhat like a junk drawer in astrophysics. It held a large and varied collection of objects whose internal compositions were poorly constrained and whose habitability potential was generally assumed to be low. Madhusudhan's team looked at this drawer differently. They asked, what if some of these worlds are not failed gas giants or supersized rocks, but something stranger and potentially more interesting? What if some of them are ocean worlds all the way down, global liquid water oceans blanketed by thick hydrogen atmospheres, And what if those conditions are, against intuition, actually conducive to life? The Hycean world concept describes a planet in the size range of 1.5 to 2.5 Earth radii, with a thick hydrogen-dominated atmosphere and a liquid water ocean covering the entire surface. Not patches of ocean like Earth's. Not a water-bearing planet where most of the surface is land. A global ocean, continuous and deep, with no significant land masses interrupting the water. Below the ocean surface, conditions would depend on depth, relatively temperate near the top, increasingly pressurized and exotic at depth, potentially reaching states of water that have no equivalent in Earth's oceans. The atmosphere above this ocean would be dense with hydrogen, the simplest and most abundant element in the universe, and the interaction between this hydrogen-rich air and the liquid surface below would create an environment unlike anywhere in our solar system. Now you might immediately think, hydrogen doesn't sound like a hospitable medium. We don't breathe hydrogen. Our biology evolved in a nitrogen-oxygen atmosphere. Hydrogen is flammable, for one thing, though it needs oxygen to combust, and in a hydrogen-dominated atmosphere without free oxygen, that particular concern doesn't apply. But the deeper question is whether any known biology, or any plausible biology we can theorize, could persist in a hydrogen-rich environment at the pressures and temperatures a Hycean world's ocean surface would present. Your mainstream historical fact, the concept of planetary habitable zones, was formalized in modern scientific terms through work by James Casting, Daniel Whitmire and Ray Reynolds in a landmark 1993 paper, which defined the continuously habitable zone as the range of orbital distances where liquid water could exist on a rocky planet's surface over geological timescales. This definition became a cornerstone of astrobiology. The Hycean world framework directly challenged and expanded this definition, arguing that the habitable zone for a hydrogen-dominated world would be substantially wider than the casting-style habitable zone, because thick hydrogen atmospheres provide dramatically more greenhouse warming than Earth's thin nitrogen-oxygen mix. Researchers are still debating the precise boundaries and the robustness of Hycean habitability models under various stellar conditions, and the question of how wide the Hycean habitable zone truly is remains genuinely open. Why does a hydrogen atmosphere expand the habitable zone? Because hydrogen is an exceptionally effective greenhouse gas. A planet wrapped in dense hydrogen retains heat far more efficiently than a planet with Earth's thin atmospheric blanket. This means a Hycean world could maintain liquid water oceans at orbital distances from its star where an Earth analogue would be a frozen ball of ice. It also means that Hycean worlds closer to their star than K2-18b might maintain liquid water on their surfaces, even under conditions we'd consider inhospitably warm, because the ocean absorbs and distributes heat with enormous efficiency. The ocean on a Hycean world would not be quiet or comfortable by any definition a human beachgoer would recognize. The atmospheric pressure at the ocean's surface beneath that thick hydrogen blanket would be substantially higher than Earth's surface pressure. The water would be warm near the top, compressed and increasingly exotic at depth, possibly transitioning into strange phases like high-pressure ice or supercritical water in the deepest regions. At the interface between the hydrogen atmosphere and the liquid water surface, the zone most analogous to Earth's ocean surface where phytoplankton thrive, conditions might actually be within the temperature and pressure range where water-based chemistry can operate, and where biological reactions we understand could theoretically proceed. This is where the Cambridge team's argument gets careful and quietly audacious at the same time. They're not claiming the entire Hycean ocean is habitable. They're proposing that specific zones, particularly the upper ocean layers near the atmosphere-ocean interface, might support microbial life. Simple, ancient, chemically resourceful. Not fish, not anything with opinions. Just the kind of single-celled organisms that were the only life on Earth for 3 billion years, and that, during those 3 billion years, successfully transformed Earth's atmosphere from hydrogen and methane to the oxygen-rich environment that eventually allowed complex life to develop. Your quirky tidbit: hydrogen, the dominant atmospheric component of a Hycean world, is so light that Earth's gravity cannot hold it in sufficient quantities. Free hydrogen in Earth's atmosphere drifts upward and is gradually lost to space. Our nitrogen-oxygen atmosphere represents, in some sense, what's left after the hydrogen ran away. Hycean worlds are more massive than Earth and can grip their hydrogen more firmly, which means that in the universal context of planetary atmospheres, the nitrogen-oxygen mix we breathe is the odd one out. Hydrogen-rich atmospheres are, statistically speaking across the galaxy, far more common. We are, atmospherically, the strange ones. The theoretical attractiveness of Hycean worlds as life-bearing candidates is significant. If Hycean worlds are common, and given how many mini-Neptunes Kepler found they likely are, and if even a modest fraction of them have temperate upper oceans, then the galaxy contains an enormous number of potentially life-bearing environments that previous habitability frameworks had essentially ignored. The search for life had been focused primarily on Earth-like rocky planets, roughly Earth-sized, orbiting sun-like stars in narrow habitable zones. Hycean worlds throw that door wide open. This is the theoretical backdrop against which the James Webb data from K218b landed. Not as a random detection, but as the potential confirmation of a carefully reasoned scientific prediction that Hycean worlds exist, that K218b is one, and that if life is in its ocean, we might be able to tell. The molecule they hoped to find, and possibly did, had already been doing something remarkable on Earth for billions of years, mostly without credit. Dimethyl sulfide has a chemical formula that sounds more like a security password than a molecule of any consequence. CH3SCH3. Two methyl groups flanking a single sulfur atom bonded together into a structure so simple and small that it barely seems worth the attention. And yet this molecule is, in several important senses, one of the things keeping Earth's climate in a livable range, and apparently one of the things that may have just announced the possible presence of life on another world 120 light-years away. Chemistry, as a discipline, has a way of making the understated do the extraordinary. On Earth, the story of dimethyl sulfide begins in the sunlit upper layers of the ocean, in the community of phytoplankton, microscopic, single-celled, photosynthetic organisms that are collectively responsible for producing roughly half of the oxygen in Earth's atmosphere. These organisms are ancient, diverse, and vitally important in ways that most people who have ever enjoyed breathing have never been required to think about. Among their many biochemical activities, phytoplankton produce a compound called DMSP, dimethyl sulfonopropionate. which functions as a cellular osmolyte, helping the cells maintain the right internal salt balance as the salinity of the surrounding seawater fluctuates with temperature, evaporation, and seasonal changes. It is essentially a molecular shock absorber for saltwater stress. When phytoplankton die, when bacteria digest them, when zooplankton eat them and break them apart, the DMSP within their cells is released into the water. Enzymes from bacteria then convert DMSP into dimethyl sulfide, DMS, which is volatile, meaning it readily evaporates from the water surface and passes into the atmosphere above the ocean. The ocean is, in this sense, constantly exhaling. Billions of tons of DMS move from the ocean into the atmosphere every year, silently, without announcement, produced by organisms so small that 1 million of them could fit on the period at the end of this sentence. Your mainstream historical fact: in 1987, 4 scientists, Robert Charlson, James Lovelock, Meinrad Andrea and Peter Brimblecombe, published a paper in Nature proposing what became known as the CLAW hypothesis. They argued that marine phytoplankton, through DMS, participate in a climate-regulating feedback loop. Warmer temperatures encourage phytoplankton growth, which produces more DMS, which creates more sulfate aerosols in the atmosphere, which seed more clouds, which reflect more sunlight, which cools the ocean, which slows phytoplankton growth. A biological thermostat. The hypothesis attracted enormous attention and generated decades of research. Scientists still debate how strong this feedback actually is in practice. Field measurements have given mixed and sometimes contradictory results, and the claw hypothesis in its original strong form has been modified considerably by subsequent data, with some researchers arguing the cooling effect is real but modest, and others maintaining it is more significant than current models suggest. Once DMS enters the atmosphere, it reacts with oxygen and hydroxyl radicals to form sulfate particles. These particles are cloud condensation nuclei, the tiny seeds around which water vapour condenses to form cloud droplets. More cloud droplets mean brighter, more reflective clouds, which bounce more sunlight back into space. The ocean life is, quite literally, engineering the clouds above itself. Whether or not this constitutes deliberate planetary engineering, and it decidedly does not because phytoplankton have no opinions about climate policy, it is a remarkable example of biology reshaping planetary-scale physical systems. Here is why this matters for K218b. DMS is, in the vocabulary of astrobiology, a biosignature molecule. A biosignature is any chemical compound, atmospheric ratio, or physical feature that is indicative of biological activity. The ideal biosignature is one that biology produces in large quantities, and that no known non-biological process generates in comparable amounts. DMS is a strong biosignature candidate precisely because on Earth, its overwhelmingly dominant source is marine biological activity. Volcanoes produce some sulfur compounds, but not significant DMS. Photochemical reactions in the atmosphere can produce some sulfur chemistry, but not, as far as we know, DMS in notable concentrations. Every substantial source of DMS we have identified on Earth traces back, one way or another, to ocean organisms. The important caveat, and the Cambridge team includes it explicitly and prominently in their paper, is that K218b is not Earth. Its atmospheric chemistry, its pressure-temperature profile, and its overall environment differ so substantially from Earth that chemical pathways which don't operate on our planet might operate there. Theoretical chemists have pointed out that in a hydrogen-rich, reducing atmosphere like K218b's, certain photochemical reactions involving sulfur compounds could potentially generate molecules with spectral signatures overlapping with DMS at the precision levels currently achievable by Webb. This possibility has not been ruled out. It is being actively researched, and it is one of the primary reasons the scientific community describes the DMS detection as intriguing rather than confirmed. Your quirky tidbit: DMS is used in small quantities in the food industry. It contributes to the savoury, slightly sweet smell of cooked corn, certain cheeses, and some types of beer. Food chemists add it deliberately to enhance flavour profiles in processed foods. The next time you eat a bowl of corn chowder or drink a particular style of Pilsner and notice that distinctive savoury note, you're experiencing trace amounts of the same molecule that may or may not indicate the presence of alien microbial ocean life orbiting a red dwarf in the constellation Leo. Food has never been more philosophically rich. You're welcome. The detection itself, or more precisely the atmospheric signal consistent with DMS, emerged from the Webb spectral data when the team analysed the molecular absorption features in K218b's atmosphere and compared them against libraries of known molecular fingerprints. The match to DMS was present, but not overwhelming. Carbon dioxide and methane in the atmosphere were detected at much higher confidence. The DMS signal sat at a level the team described as suggestive, present enough to include in the paper, not strong enough to declare definitive. The 99.7% headline figure attached to the K2-18b story refers to a broader claim about the presence of carbon-bearing molecules overall, not to DMS specifically. This distinction is important, and it leads us naturally to the question that the 99.7% number raises in anyone who stops to think about it carefully. What does 99.7% confident actually mean? And why does a number that sounds almost certain still leave serious scientists talking in the careful language of possibility rather than fact? The technique that Webb used to read K218b's atmospheric chemistry is one of those scientific methods that sounds, on first description, almost too elegant to be real. It is called transmission spectroscopy. It works like this. When a planet passes in front of its host star, an event called a transit, which happens with clockwork regularity because orbital mechanics are nothing if not punctual, the planet blocks some of the star's light. The dip in brightness is small but measurable. However, the planet is surrounded by an atmosphere, and this atmosphere, thin as it is relative to the planetary body itself, extends beyond the solid disk of the planet and acts as a transparent but not quite transparent halo through which the star's light must pass. As the star's light filters through this atmospheric halo during transit, specific molecules in the atmosphere absorb specific wavelengths of that light. Carbon dioxide absorbs infrared wavelengths in a particular pattern. Methane absorbs a different set of wavelengths. Water vapour has its own fingerprint. Dimethyl sulfide has its own. Each molecule removes a specific set of wavelengths from the starlight that passes through it, like pressing specific keys on a piano. The resulting chord is unique to the molecule pressing it. By measuring which wavelengths are missing from the star's light when the planet is in transit, compared to the full spectrum when no planet is blocking the view, scientists can read a list of molecules present in the atmosphere. It is, in the most literal sense, reading an alien chemistry set by the light it casts. Your mainstream historical fact: the first successful detection of an exoplanet atmosphere using transmission spectroscopy was achieved in 2001, when a team led by David Charbonneau used the Hubble Space Telescope to detect sodium in the atmosphere of HD 209458b, a hot Jupiter orbiting a star about 159 light-years away. The detection was considered a landmark achievement at the time. Today, with Webb, the same fundamental technique has been refined to the point where we can detect trace molecular constituents in the atmospheres of planets as small as K218b at comparable distances. A leap in capability so vast that it makes the 2001 sodium detection look like reading a billboard while Webb reads the fine print instructions on a pharmaceutical package insert. Science advances with a speed that routinely embarrasses its own previous ambitions. The instrument aboard Webb primarily responsible for the K218b analysis is called NIRSpec, the Near-Infrared Spectrograph, built by the European Space Agency. NIRSpec can simultaneously observe up to 100 separate objects and covers a wavelength range from 0.6 to 5.3 micrometers. This range encompasses the absorption signatures of most atmospherically relevant molecules, including water, carbon dioxide, methane, carbon monoxide, and dimethyl sulfide. Webb's second contributing instrument for this work is MIRI, the mid-infrared instrument, which covers longer wavelengths and contributes additional diagnostic power for certain molecular species. Together, these instruments give scientists a wide spectral window into K218b's atmospheric composition, with sensitivity that would have seemed fantastical to astronomers even 15 years ago. The process of translating a raw Webb spectrum, the instrument's raw output, which looks like a graph of light intensity versus wavelength, into specific molecular identifications is computationally intensive and methodologically careful. Scientists use atmospheric retrieval algorithms, which work by generating millions of simulated spectra for different assumed atmospheric compositions, temperatures and pressures, and then statistically identifying which simulated atmosphere best matches the observed data. It's like trying to identify a song by humming a melody you only half remember into a database of every song ever recorded. Except the database contains every possible atmosphere ever modelled, and getting the wrong answer has implications for the history of a life in the universe. No pressure. Your quirky tidbit, the same physical principle underlying transmission spectroscopy, light filtered through a medium absorbing specific wavelengths, is also how roadside breathalyzers work. Infrared light passes through a sample of breath. Ethanol molecules absorb specific wavelengths. The device measures the missing wavelengths and calculates blood alcohol concentration. In the most technically literal sense possible, James Webb is administering a breathalyzer test to K2-18b at a distance of 120 light-years. Please breathe into the spectrograph K2-18b. You've been flagged for atmospheric screening. K2-18b's result. Possibly biologically intoxicated. The K2-18b analysis required multiple transit observations stacked together. Webb observed K2-18b transiting its host star several times, combining the data to build up signal-to-noise ratio, the ratio of genuine signal to random noise, to the point where molecular identifications could be made with statistical confidence. A single transit observation provides some information, but stacking multiple transits dramatically sharpens the picture. The Cambridge team's analysis involved careful correction for instrumental systematic errors, for the star's own spectral characteristics, and for the many ways a spectrum can mislead if not treated with scrupulous methodology. The question of how reliable atmospheric retrievals are for Hycean worlds specifically is one the community is actively working through. Standard retrieval frameworks were developed for hot Jupiters, large, hot, gas giant exoplanets with thick, relatively simple atmospheres that are relatively easy to model. K218b, with its cooler, potentially cloud-bearing, chemically complex Hycean atmosphere, requires models that are still under active development. Several research groups have noted that different atmospheric model assumptions, different treatments of clouds, different temperature pressure profiles, can shift the inferred molecular abundances, potentially affecting which molecules appear significant. Scientists continue to debate the precise robustness of the K218b retrieval, particularly for the DMS component. What is certain, regardless of these details, is that Webb is doing something no telescope before it could do, reading the atmospheric chemistry of small, potentially habitable exoplanets in the real, tangible sense of identifying specific molecules with statistical confidence. The technique works. The machine works. It is providing data that, for the first time, puts the question of biosignatures on other worlds in the domain of observation rather than speculation. Whether the specific K218b data contains a genuine DMS detection or not, the era of atmospheric biosignature searches has begun. The era of hoping someone would invent a way to do this is over, and that, whatever else happens with this particular planet, is revolutionary. 99.7%. Those four characters have been sitting in the back of your mind since they first appeared, and they deserve careful handling. Because 99.7% sounds in everyday language like virtual certainty. If a surgeon told you a procedure had a 99.7% success rate, you'd schedule it without serious hesitation. If a meteorologist told you there was a 99.7% chance of rain tomorrow, you would not be surprised to find yourself wet. If a game show told you that a door had a 99.7% chance of containing the prize, you would open it with confidence bordering on smugness. In daily life, 99.7% is functionally indistinguishable from certainty. In science, 99.7% is where the serious conversation begins. The language scientists use for confidence is built on a unit called sigma, the Greek letter sigma, which represents standard deviations in a statistical distribution. A result at 1 sigma is 68% likely to be real. 2 sigma, about 95%. 3 sigma, which corresponds to 99.7%, is the threshold most sciences use to declare something evidence, strong enough to take seriously, warrant follow-up, and publish in a peer-reviewed journal. But 3 sigma is explicitly not sufficient for a discovery claim in the most rigorous scientific sense. For that, the standard in physics is 5 sigma, roughly 99.99994% confidence, or odds of 1 in 3.5 million that the result is a statistical fluke. Your mainstream historical fact, the discovery of the Higgs boson, announced jointly by the ATLAS and CMS experiments at CERN's Large Hadron Collider on July 4, 2012, met the 5 sigma threshold simultaneously in 2 independent experiments, providing essentially unambiguous confirmation. The boson had been theoretically predicted by Peter Higgs and 5 other physicists in 1964, making the gap between prediction and experimental confirmation 48 years. When the announcement was made in an auditorium at CERN packed with physicists and scientists, Peter Higgs himself was present, and according to multiple accounts, was visibly and genuinely moved. He told reporters afterward that he had never expected to see the experimental confirmation in his lifetime. Particle physicists, who are not generally known for public emotional displays, struggled to maintain composure. Scientists still debate fine details of the measured Higgs properties that don't perfectly match the Standard Model's cleanest theoretical predictions, meaning even the most celebrated confirmed particle in physics history retains open questions. Now, the 99.7% figure in the K2-18 B paper requires a very specific reading. The 3 sigma confidence reported by the Cambridge team applies to the detection of carbon-bearing molecules in K2-18b's atmosphere, primarily methane and carbon dioxide. This is the headline statistical figure. The DMS detection is stated separately and at a lower confidence level, described by the authors as tentative and requiring further observational confirmation. The leap from 99.7% confident in atmospheric molecular detections to 99.7% chance of life that populated headlines was a journalistic shortcut that compressed a nuanced, multi-step argument into a number attached to a conclusion the scientists themselves had carefully not drawn. To their credit, Madhusudan and his co-authors were admirably clear in the paper itself. They explicitly state that the DMS detection is consistent with but not established by the current data, that abiotic production of DMS cannot be ruled out, and that follow-up observations are needed. The 99.7% was adopted by headlines because it's a compelling number, and compelling numbers do compelling things to news cycles. The scientists had done their job properly. The communication layer between scientists and public had done what it typically does: simplified, amplified, and attached the most dramatic interpretation to the most impressive sounding figure. Here is your quirky tidbit. The 0.3% probability of being wrong at 3 sigma significance means that if scientists ran 1,000 independent 3 sigma detection experiments, approximately 3 of those experiments would report a false positive, even if every scientist did everything correctly. This is not a flaw in science. It is a property of statistical inference that science openly acknowledges and builds safeguards against. The safeguard is replication. Repeat the observation, ideally with independent instruments and independent teams, until the result either strengthens or dissolves. The K2-18b result is currently in the replication phase. More Webb observations are scheduled. Independent teams are analysing the same data. The conversation is not over, it has barely started. What does 99.7% actually give you then, if not certainty? It gives you permission from the mathematics of probability, to take a result seriously, invest resources in following it up, and build a scientific program around investigating it further. It says, this is not noise. This is not an artifact we can dismiss. Something is here that deserves our best instruments, and our most careful attention. That is precisely the right response to a 3 sigma result. Not celebration, not dismissal. Focused, rigorous follow-up. The reaction within the astrophysics community illustrated this well. The paper was received with genuine excitement, because a possible DMS detection on a Hycean world is genuinely exciting, and with immediate healthy skepticism, papers appeared in the weeks and months following, examining the atmospheric retrieval methodology, questioning whether alternative molecular combinations could explain the spectrum without DMS, and probing the models used for the Hycean atmosphere. Some of those papers supported the team's conclusions, others raised concerns that they acknowledged merited further investigation. Scholars are still actively debating the robustness of the DMS component of the detection. This is science functioning exactly as it should. Not a unanimous chorus, not a declaration of victory, a structured argument between careful people using the best available evidence, with more evidence on the way. Science has a long, occasionally humbling relationship with announcements that turned out to be premature. In 1967, astronomer Jocelyn Bell was analysing radio telescope data at Cambridge, the same institution, fittingly, where the K218b paper would emerge decades later, when she noticed a signal so precise and regular it seemed impossible for nature to produce. The pulses arrived every 1.33 seconds with a clockwork regularity that no known natural source could match. The Cambridge team quietly designated the source LGM1. LGM stood for Little Green Men. They weren't joking, at least not entirely. The signal was so extraordinary that the possibility of an artificial intelligent origin had to be considered. It turned out to be the first pulsar ever detected, a rapidly spinning neutron star emitting beams of radio waves from its magnetic poles like a cosmic lighthouse. Nature, it emerged, could produce extraordinary clockwork without any help from intelligence. Then came ALH 84001, the Mars meteorite found in Antarctica in 1984, believed to have been blasted off Mars by an ancient impact and eventually captured by Earth's gravity after wandering the solar system for roughly 15 million years. In 1996, a NASA-led team published a paper in Science arguing that the meteorite contained several lines of evidence for ancient Martian microbial life, polycyclic aromatic hydrocarbons associated with biological decay, magnetite crystals resembling those produced by Earth bacteria, carbonate globules that suggested biological deposition, and, most visually dramatic, tiny, elongated structures resembling microfossils. The announcement was accompanied by a statement from President Bill Clinton, which is not normally how peer-reviewed science operates. Scientists still debate the ALH 84001 evidence to this day. The mainstream view is that all the features have plausible non-biological explanations, but a small number of researchers continue to argue that the totality of evidence remains suggestive of ancient biology, and the question has never been definitively closed. The skeptic's case against the K218b DMS detection is serious and worth laying out honestly, because dismissing it would be both intellectually dishonest and bad practice for anyone who wants to think clearly about what we actually know. The skeptics are not people who don't want life to exist elsewhere. They're people who understand that the history of astrobiology is littered with detections that didn't survive scrutiny, and who apply the principle that extraordinary claims require extraordinary evidence. Your mainstream historical fact, In 2010, NASA held a press conference announcing a discovery that would, they said, impact the search for extraterrestrial life. The result was a paper claiming that a bacterium from Mono Lake, California, a highly alkaline arsenic-rich environment, could substitute arsenic for phosphorus in its DNA and other biological molecules. If true, this would mean life can use a fundamentally different elemental toolkit than previously thought, dramatically expanding the range of environments where life might arise. The paper attracted fierce and well-organized scientific criticism almost immediately. Multiple research groups failed to replicate the finding. The scientific consensus shifted rapidly toward the conclusion that the original analysis contained significant methodological errors, and the arsenic life claim is now regarded by most astrobiologists as incorrect. The incident became a frequently cited example of why extraordinary claims in astrobiology require extraordinary patience before public announcement. The first skeptical argument against the K2-18 BDMS result concerns the possibility of abiotic DMS production. On Earth, significant abiotic production of DMS is unknown. Every major source traces back to biology. But K2-18b is a hydrogen-rich reducing atmosphere world under conditions that have no terrestrial analogue. Theoretical atmospheric chemists have proposed that in such an environment, photochemical reactions involving sulfur, which may be present in the atmosphere from volcanic outgassing or other geological sources, could potentially produce sulfur-containing compounds whose infrared absorption signatures overlap with DMS's at the spectral resolution currently achievable by Webb. This hasn't been demonstrated experimentally. The detailed photochemical modelling for Hycean world atmospheres is still under development, but the possibility exists and cannot yet be ruled out observationally. The second concern involves the atmospheric retrieval models. To convert a Webb spectrum into molecular identifications, scientists must compare observed spectra against model spectra generated by simulating an atmosphere with assumed composition, temperature profile, cloud properties, and other parameters. The best fit model is the one whose simulated spectrum most closely matches the observation. For K2-18b, the retrieval framework was adapted from methods developed primarily for hot Jupiter atmospheres, a very different physical regime. Hycean-specific retrieval models are newer and less tested. Different research groups applying different model assumptions to the same Webb data have arrived at somewhat different conclusions about the molecular abundances in K2-18b's atmosphere, which suggest that the modelling uncertainties are non-trivial. The DMS identification, being a trace constituent at the margins of detectability, is the component most sensitive to these modelling choices. Your quirky tidbit. False positive signals in spectroscopy have an informal name in the field: spectral ghosts. They arise when one molecule's absorption features overlap with another's, when instrument noise mimics a real chemical signal, or when the molecular databases used for comparison contain small inaccuracies from laboratory measurements. The primary molecular database used in infrared astronomy, called Hycean, contains absorption data for thousands of molecules compiled from laboratory measurements, and it is regularly updated as new experiments refine the values. If any entry in Hycean is even slightly wrong, every atmospheric analysis using that entry inherits the error invisibly. Hunting ghosts is painstaking work. The third concern is the weakness of the DMS signal itself. The Cambridge team, to their credit, states this explicitly. The DMS component of the spectrum is the most uncertain element of their analysis. The carbon dioxide and methane detections are robust. The DMS signal is at a level where the team describes it as consistent with the data, but not required by it, meaning a model without DMS but with different assumptions about other molecules might fit the observations nearly as well. This is not dishonesty. It is precision, but it is also an invitation to the field to look harder. The honest answer to "could this be a false alarm?" is yes, possibly. The honest answer to "should we keep looking?" is absolutely yes. Both of these answers are correct simultaneously, and holding them both at once is what scientific literacy requires. The word life is doing a lot of work in tonight's story, and it deserves a moment of careful inspection, because it turns out to be a word that science uses with less certainty than you might expect. You've used this word thousands of times without thinking about it. The plants on your windowsill are alive. The bacteria multiplying in your gut at this very moment, roughly 40 trillion of them, more numerous than your own body's cells, are alive. You're alive, presumably, though by hour 14 of a sleep deprivation experiment, this becomes more of a philosophical position than a confident empirical claim. But what exactly distinguishes living things from non-living things? Biology has tried for centuries to provide a clean definition, and the attempts are consistently both informative and slightly unsatisfying. The most common working definition requires several properties: metabolism, the ability to consume energy and use it to perform biological work; reproduction, the ability to create copies of oneself; response to stimuli, the ability to detect and react to environmental changes; homeostasis, the ability to maintain stable internal conditions despite external variation; and growth and organization, the development of structured complexity from simpler starting materials. Some definitions add evolution, the ability to change over generations through natural selection, as an essential feature. These criteria do what they're supposed to do. They include bacteria, plants, fungi, animals, and every other organism we've studied. They also produce some inconvenient edge cases. Viruses meet some criteria. They carry genetic information. They reproduce. But they cannot metabolize independently and require a host cell to replicate. Fire counterintuitively metabolizes, reproduces by spreading, and responds to its environment by consuming whatever fuel is available. Fire is not alive. The definition is functional but imperfect, and every biology textbook acknowledges this in its own quietly embarrassed way. Your mainstream historical fact, the Miller-Urey experiment of 1952, is one of the most celebrated demonstrations in the history of origin of life research. Stanley Miller, a graduate student working under Nobel laureate Harold Urey at the University of Chicago, assembled a closed flask system filled with methane, ammonia, hydrogen, and water vapor, compounds believed at the time to represent Earth's primordial atmosphere, and subjected the mixture to electrical sparks simulating lightning. After running the experiment for 1 week, he analyzed the products and found amino acids, the fundamental building blocks of proteins, the molecular machinery of life, arising spontaneously from inorganic chemistry under simulated early Earth conditions. It was a stunning demonstration that life's molecular components could emerge from non-living chemistry. Scientists still debate whether Miller and Urey correctly reproduced early Earth's atmospheric chemistry. Subsequent research suggests the early atmosphere was more carbon dioxide rich and less reducing than their setup. But the core finding that organic complexity arises naturally from simple chemistry under appropriate conditions has never been seriously challenged. The study of extremophiles, organisms thriving where life was previously thought impossible, has relentlessly expanded the envelope. Tardigrades, those microscopic water-dwelling animals sometimes called water bears, can survive the vacuum of space, radiation levels thousands of times lethal to humans, temperatures ranging from minus 272 degrees to over 150 degrees Celsius, and pressures 6 times greater than the deepest ocean trench. Deinococcus radiodurans withstands radiation doses that would destroy human DNA 1,000 times over, because it repairs its genome at extraordinary speed. Archaea colonize hydrothermal vents on the ocean floor, living in temperatures above boiling water, in total darkness, deriving energy from chemical reactions between volcanic fluids and seawater. Every time biology has encountered a supposed limit, it has found organisms already there, apparently unbothered, operating in ways that required the textbooks to be updated. This matters for K218b because it tells us something important. Life on Earth is not fragile, it is tenacious. It occupies every environment where it can extract energy, access liquid water, and perform the chemical reactions its metabolism requires. The oceans of a Hycean world, warm, liquid, chemically complex, potentially rich in dissolved minerals from geological activity below, might represent exactly the kind of environment where microbial life, if it arose, could find a foothold. But here is the deeper, stranger question. Must life anywhere in the universe look chemically like life here? Must it use water as a solvent? Must it rely on carbon as the backbone of its molecular architecture? Must it use DNA to encode information? There are serious scientific reasons for believing that carbon and water are the most plausible basis for life anywhere. Carbon's unmatched ability to form complex molecules, water's exceptional properties as a chemical solvent. But most plausible is not only possible. Your quirky tidbit. Some researchers have proposed that life could theoretically function in liquid methane, as might exist in the lakes of Titan, Saturn's largest moon. Such life would breathe hydrogen instead of oxygen, metabolize acetylene instead of glucose, and produce methane as a metabolic waste product. It would be so chemically alien that our standard biological detection methods, which are calibrated to find Earth-type biochemistry, might not recognize it even if instruments were operating correctly. This hypothetical category is sometimes called shadow biosphere, or weird life, and while no confirmed example exists anywhere, the theoretical argument for its possibility has been seriously made by seriously credentialed scientists. For K218b specifically, the life being hypothesized is not weird life or shadow life. The DMS signal, if real and biological, implies organisms producing DMSP chemistry, marine microbes operating on broadly familiar biochemistry, carbon-based, water solvent, metabolizing and excreting in ways Earth biology has precedent for. In a sense, the most remarkable thing about the K2-18b hypothesis is not how strange the proposed life is, but how familiar. Just ocean microbes, doing what ocean microbes do, 120 light-years away under a red sun, producing the same molecule that makes Earth's beaches smell the way they do. Life, if it's there, is probably not so different from what's living in a spoonful of seawater right now. Small, ancient, chemically clever, entirely indifferent to the fact that it has made astronomers on a pale blue dot very nervous and very excited. The desire to find life beyond Earth is not a product of the space age. It predates the telescope, predates the printing press, and is, in the most honest assessment, probably as old as the first human mind that looked up at the night sky and recognized it as something vast rather than merely decorative. The stars have always invited the question. The question is embarrassingly old. In the 5th century BCE, the Greek philosopher Democritus, the same thinker who proposed that matter was composed of indivisible units he called atoms, which turned out to be essentially correct, argued that the universe contained an infinite number of worlds, and that many of them must contain living creatures. He had no telescope. He had no data. He had philosophical reasoning and a powerful intuition that an infinite universe producing life in one place would probably produce it in others. He was working purely from logic. He may have been right. Giordano Bruno, the Italian friar and philosopher, pushed the idea further in the 16th century. Not merely other worlds, but other worlds orbiting other suns, many of them inhabited by beings we couldn't imagine. This was not a casual observation. In the cosmological framework of the Roman Catholic Church, Earth was the unique, divinely appointed centre of a finite universe, and the suggestion of infinite inhabited worlds was a direct challenge to the architecture of the faith. Bruno was tried by the Inquisition and burned at the stake in Rome in 1600. Historians still debate exactly which specific beliefs led to his execution, and the relative weight the Church placed on his cosmological views versus his theological heterodoxies. The historical record on the precise charges is complex and contested, but his death stands as the most extreme illustration in history of how threatening the idea of other inhabited worlds can be to a worldview built on cosmic uniqueness. By the 17th century, Christian Huygens, the Dutch mathematician and astronomer who discovered Saturn's rings and Titan, was writing seriously about the inhabitants of Jupiter and Saturn, imagining beings adapted to their different environments. William Herschel, the 18th century astronomer who discovered Uranus, and was by any measure one of the greatest observational astronomers in history, believed quite sincerely that the Sun was inhabited by beings adapted to its fiery surface, sheltered perhaps by a cool cloud layer beneath the solar atmosphere. This was not a fringe view. It was a respectable position shared by several scientists of his era, all of whom were reasoning from the principle that whatever forces produced life on Earth would likely produce it wherever conditions allowed. Then data arrived, and some dreams closed. Mars had no canals. Percival Lowell's magnificent vision of Martian waterworks dissolved under better telescopes and eventually spacecraft. Venus, long imagined as a lush jungle world beneath its clouds, turned out to be a hellscape of 460-degree temperatures and acid rain. The Moon was an airless, waterless, magnificently desolate rock. As the 20th century spacecraft reached each neighbouring world and sent back the unflattering truth, the solar system seemed progressively emptier of company. Your mainstream historical fact, the modern scientific search for extraterrestrial intelligence, began formally in 1960, when Frank Drake pointed the 85-foot radio telescope at Green Bank, West Virginia, at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial radio signals. He heard nothing definitive, but he had started something that did not stop. SETI, the search for extraterrestrial intelligence, which has been running in various forms ever since. In 1961, Drake formulated the Drake equation, a mathematical framework for estimating the number of communicating civilizations in the Milky Way by multiplying together a chain of probabilities from the rate of star formation to the average lifetime of a technological civilization. Most of the terms in the equation were unknown in 1961 and remain uncertain today, making the equation less a calculation than a structured way of identifying what we don't know. Your quirky tidbit: in the summer of 1977, a volunteer named Jerry Eman was reviewing radio telescope data printouts from Ohio State University's Big Ear telescope when he spotted an anomalous signal of extraordinary strength, so unusual it lasted exactly 72 seconds, the maximum possible duration given the telescope's observation geometry. Eamon circled the signal on the printout and wrote a single word in red pen next to it. Wow. The wow signal has never been detected again, never definitively explained, and never definitively attributed to any natural astrophysical source. It remains, 40+ years later, one of the most discussed anomalies in the history of SETI, a signal that might have been everything and might have been nothing, sitting in an old printout in an archive still waiting. The decades between Lowell's Canals and James Webb's Golden Mirror saw the growth of astrobiology as a formal discipline, the scientific study of the origin, distribution and future of life in the universe. NASA established an astrobiology program, research institutes formed, the journal Astrobiology began publication. The field developed a theoretical toolkit, biosignatures, habitability frameworks, origin of life models, planetary atmospheric chemistry, all of it in service of the same question that Democritus worked on with nothing but a sharp mind and a dark Greek night above him. The detection of more than 5,000 exoplanets by Kepler and successor missions changed the numbers decisively. Before Kepler, the question, how many habitable planets are there in the galaxy, had enormous error bars because we didn't know if planets were common or rare. After Kepler, we know planets are ordinary. Nearly every star has them. The Milky Way contains roughly 100 billion stars, and estimates suggest hundreds of billions of planets, with tens of billions potentially inhabitable zones. The raw material for life, or at least for the conditions where life could arise, is not scarce. Against this backdrop, the K2-18b finding lands differently than Lowell's Canals or the WOW signal. It is not an observer deciding they see what they hope to see. It is an instrument of unprecedented precision detecting a molecular signal in a physically plausible location using a technique validated on dozens of previous targets. The history of the search for alien life is full of false starts. But history also has a direction, and the direction is toward better tools and better data. Webb is the best tool we've ever had, and its data is pointing somewhere interesting. In the summer of 1950, the physicist Enrico Fermi was walking to lunch at Los Alamos National Laboratory with colleagues, having just seen a cartoon in The New Yorker depicting aliens stealing New York City's trash cans. The conversation drifted. as conversations with Fermi tended to do, toward a serious question embedded in a silly image. If the galaxy is old, and if life is not rare, and if some fraction of life-bearing planets produce civilizations that develop technology, then some of those civilizations must be far older than ours, millions or billions of years older. And if they exist, and if some of them have had the time and the means to spread across the galaxy, where are they? Where are the signals, the artifacts, the visitors, the evidence? Fermi reportedly looked at his colleagues over his lunch tray and asked, with the directness that characterized his approach to physics, and apparently also to cosmic demographics, "Where is everybody?" This became known as the Fermi paradox. It is one of the most productive and most unsettling ideas in the history of science. A question, really, rather than a paradox in the strict logical sense, but a question so pointed and so well framed that it has generated decades of serious research and an entire genre of increasingly alarming proposed solutions. The paradox rests on a tension between two observations. First, that the galaxy is ancient enough and large enough that if intelligent life is not extraordinarily rare, some civilizations should have had billions of years to spread across it, or at minimum make their presence detectable. And second, that we observe none of this. No alien signals in our radio telescopes, no megastructures orbiting nearby stars, no artifacts in the solar system, no visitors. A galaxy that looks from every direction we've pointed our instruments, functionally empty of evidence for intelligence. Either intelligent life is extraordinarily rare, or there is some systematic reason we can't detect it, or there is some systematic reason that civilizations don't spread or signal, and none of the options are entirely comfortable. Your mainstream historical fact, the Drake equation proposed by Frank Drake in 1961, provides a framework for estimating the number of communicating civilizations in the Milky Way at any given time. Its terms multiply together the rate of star formation, the fraction of stars with planets, the fraction of planets in habitable zones, the fraction where life arises, the fraction where intelligence develops, the fraction that become communicating civilizations, and the average lifespan of such civilizations. As of the mid-2020s, the first three terms are reasonably well constrained by exoplanet research. Star formation rates are known. Most stars have planets, and the fraction of those planets in habitable zones is estimated at something between 10 and 50%. The remaining terms, particularly the fraction of habitable planets where life actually arises, which is the term K218b's detection would directly address, remain deeply uncertain. Now here is where K218b makes the Fermi paradox significantly louder, not quieter. If the DMS detection on K218b represents genuine biological activity, it suggests that life arose on a Hycean world 120 light-years away. Astronomers estimate there are likely tens of billions of Hycean-type worlds in the Milky Way. If life arises on even a modest fraction of them, the galaxy should be teeming with living worlds. And if life is that common, then the fraction of habitable planets where life arises, the most uncertain term in Drake's equation, might be large, perhaps even close to 1. Life might not be a cosmic accident, but a cosmic expectation, which makes the silence of the galaxy considerably more mysterious. Your quirky tidbit. One proposed resolution to the Fermi paradox is called the Great Filter. The idea that somewhere along the path from simple chemistry to spacefaring civilization, there is a catastrophically difficult step that almost nothing survives. If the great filter is behind us, in our past perhaps represented by the difficulty of the first self-replicating molecule or the development of the eukaryotic cell, then we are survivors of a rare event and the silence is explained. If the great filter is ahead of us, some challenge that civilizations consistently fail to survive, then the universe's silence is not reassuring. It is a warning. The philosopher Nick Bostrom wrote that if we ever find evidence of microbial life on another world, we should be deeply concerned rather than jubilant, because simple life would suggest the great filter lies ahead. K218b's possible microbes might, if Bostrom's logic holds, be the worst news in human history wearing an exceedingly pretty molecular dress. The proposed solutions to Fermi's paradox range from reassuring to chilling. The rare earth hypothesis suggests that the specific conditions for complex life on Earth, a large moon stabilizing our axial tilt, a Jupiter-sized planet deflecting asteroids, plate tectonics recycling nutrients, a stable star, the right chemistry at the right time, are so unlikely to combine elsewhere that complex life is genuinely rare even if microbial life is common. The zoo hypothesis suggests advanced civilizations know we're here but have chosen not to interfere, observing from a distance the way humans observe animals in wildlife reserves. The dark forest theory, popularized in Liu Cixin's novel of the same name but based on serious game theoretic arguments, proposes that the silence reflects a rational survival strategy. Civilizations that announce themselves in a universe where resources are finite and intentions cannot be verified invite destruction, so all advanced civilizations stay quiet. None of these are fully satisfied. The universe's silence in the face of what increasingly looks like the common occurrence of life-sustaining conditions is one of the deepest open questions in science. And if K218b's DMS signal holds up, the silence becomes stranger still. Microbial life in a Hycean ocean 120 light-years away. Tens of billions of similar worlds. And yet the radio spectrum is empty, the solar system is unvisited, the night sky contains no megastructures. Where is everybody indeed? Let's do something that science rarely permits and narrative occasionally demands. Let's imagine. Not irresponsibly, not in the way that Percival Lowell imagined Martian canal engineers and ran slightly too far with it, but carefully, bounded by what physics and chemistry and biology allow us to reasonably extrapolate. What might life in the ocean of K218b actually look like? The ocean itself, as far as theoretical models of Hycean worlds allow us to reconstruct it, would be dark, very dark. K218, the host star, is a red dwarf, a cool, dim star that emits most of its light in the red and near-infrared part of the spectrum, rather than the yellow-white light our own sun produces. Even at the surface of K218b's ocean, the light would be a deep, reddish twilight, and it would dim rapidly with depth. Earth's ocean is dark below a few hundred meters even under a bright yellow sun. K218b's ocean, under a dim red star, would be biologically dark and much shallower. Photosynthesis, the process by which Earth's plants and phytoplankton convert sunlight into chemical energy, would be possible near the surface, but would need to be tuned to the available wavelengths. And here's a remarkable thing. photosynthesis on Earth is already tuned. Chlorophyll absorbs red and blue light efficiently, reflecting green, which is why plants are green. Some bacteria use bacteriochlorophyll, which is tuned to absorb near-infrared wavelengths. Life on K218b, if it photosynthesizes at all, would likely be tuned to absorb the deep red and near-infrared wavelengths that K218 emits most abundantly. Theoretical biologists have called this black vegetation, organisms so optimized for absorbing their star's dim light that they would appear nearly black to a human eye, soaking up every available photon like living solar panels. The ocean surface of K218b, if covered in photosynthetic organisms, might look black or deep purple to an observer floating above it, not green. Your mainstream historical fact, the discovery of hydrothermal vent ecosystems in 1977 by oceanographers aboard the research vessel Alvin, fundamentally changed our understanding of where life can exist. Before that discovery, it was assumed that all complex life ultimately depended on sunlight, that ecosystems were powered by photosynthesis at their base. The vent communities were the first known ecosystems powered entirely by chemosynthesis. Microorganisms extracting energy from chemical reactions between hydrothermal fluids and seawater, with no sunlight required. The implications for astrobiology were immediately recognized. Any world with liquid water and geochemical activity could potentially support life, regardless of distance from its star or depth of its ocean. Researchers are still debating the full diversity of metabolic strategies employed by deep-sea vent organisms, and new vent communities continue to be discovered with unexpected biological compositions. Below the photic zone of K218b's ocean, the relatively thin layer near the surface where light penetrates, life would need to rely on chemistry rather than light. On Earth, deep-sea microbes thrive on gradients between oxidizing and reducing chemical environments, where hydrogen meets oxygen, where methane meets sulfate, where iron-rich fluids from geological sources meet the cooler ocean above. K218b's ocean, sitting above a geologically active seafloor heated by the planet's internal energy, could have hydrothermal venting providing exactly these chemical gradients. The vent communities could be extensive, diverse and ancient, organisms that have been quietly metabolizing since the planet cooled enough to support liquid water, never knowing or caring about the star above them or the golden telescope orbiting a planet 120 light-years away. The organisms producing DMS, if they're there, would be analogous to Earth's phytoplankton, near-surface organisms exploiting whatever dim light or chemical energy is available, producing DMSP as a stress compound, releasing DMS when they die or are consumed. They would be small, they would be single-celled, they would be extraordinarily ancient by the time any hypothetical intelligence elsewhere in the galaxy noticed them, and they would be busy in the way that microbes are busy, which is to say, relentlessly, without rest or awareness, dividing and eating and dying and collectively producing a planetary-scale atmospheric signal detectable across more than 100 light-years of space. Your quirky tidbit: Earth's earliest photosynthesizing organisms, ancient cyanobacteria, were responsible for one of the most catastrophic events in the history of life on this planet. Around 2.4 billion years ago, they began producing oxygen as a metabolic waste product in quantities so large that they poisoned the atmosphere for most life then existing, which had evolved in an oxygen-free world. This event, called the Great Oxidation Event, killed off vast numbers of species and reshaped the chemistry of Earth's atmosphere permanently. It was also ultimately what made complex animal life possible, including humans. The moral of this story is that microbial organisms casually reshape planetary conditions while remaining entirely indifferent to the consequences, which is either humbling or terrifying depending on whether you're a large animal thinking about it afterward. The ocean of K218b in this scenario would be ancient, probably billions of years old. Life, if it arose early in the planet's history, as it apparently arose very early on Earth, would have had enormous time to diversify and colonize every available niche. The deep vents, the twilight surface zone, the chemical gradients at the atmosphere-ocean interface, layers of microbial mats on whatever solid surfaces exist. A biosphere not visible from space in any optical telescope, not announcing itself with radio waves or city lights, but breathing quietly into its hydrogen atmosphere, releasing a molecule that carries the smell of the sea, waiting patiently for someone with a golden mirror and enough patience to notice. We noticed. K218, the star that K218b orbits, is not like our Sun. Understanding the star is essential to understanding the planet, because a star is not just a light source or a heat lamp for the worlds around it. It is the dominant environmental force in a planetary system, setting the energy budget, shaping the atmosphere, determining the radiation environment, and, in the case of red dwarfs specifically, occasionally doing things to nearby planets that our own relatively placid Sun would never dream of. K218 is a red dwarf, technically classified as an M dwarf, with a mass roughly 36% of the Sun's and a luminosity only about 3% of the Sun's. This makes it dim. Genuinely, significantly dim. In terms of visible light output, K218 is so faint that if you stood on a theoretical platform above K218b's atmosphere, the star would appear as a reddish disk somewhat larger in the sky than our Sun appears from Earth, but the light would be deep red and far less intense. Not the warm yellow of a summer noon, more like the last few minutes before sunset, but consistently as the planet's perpetual sky tone. Red dwarfs are, however, deceptive in their apparent dimness. They are not gentle. Young red dwarfs in particular, and even middle-aged ones, are prone to flares, sudden, explosive releases of energy from the stellar surface that can, in extreme cases, emit hundreds or thousands of times the star's normal energy output in a matter of minutes. These flares release intense ultraviolet radiation and X-rays, and for planets in the habitable zone of a red dwarf, which must orbit close in due to the star's low luminosity, these flares can be devastating. Intense UV and X-ray bombardment can strip atmospheric gases away over geological time, erode ozone layers that protect surface life, and potentially sterilize the upper layers of an ocean. Your mainstream historical fact, the study of the effects of stellar flares on exoplanet atmospheres and habitability, has grown substantially since the mid-2000s, driven partly by observations of M-dwarf flare activity from telescopes including Kepler, TESS, and the Hubble Space Telescope. The TRAPPIST-1 planets, those frequently discussed potential Earth analogues around another red dwarf, have been specifically scrutinized for flare exposure, and researchers have calculated that their surfaces receive substantially higher doses of high-energy radiation than Earth's surface. Scientists still debate whether the atmospheric conditions on such planets can survive long-term flare exposure, or whether habitable zones around red dwarfs are fundamentally more hostile than the classical definition implies, making the search for life around these very common stars simultaneously more promising in terms of quantity and more uncertain in terms of actual habitability. There is another structural challenge for K218b that relates to its closeness to its star: tidal locking. A planet orbiting very close to a star experiences a gravitational gradient. The side of the planet facing the star is pulled more strongly than the far side, which over geological time can lock the planet's rotation, so that one hemisphere permanently faces the star and the other permanently faces away. Earth's moon is tidally locked to Earth in exactly this way, which is why we only ever see one face of the moon. If K218b is tidally locked to K218, which is plausible given its orbital period of 33 days, then one hemisphere experiences permanent day side with continuous star illumination, and the other is in permanent night side darkness. For a rocky planet, tidal locking creates dramatic climate contrasts: a roasting day side, a freezing night side, and potentially violent atmospheric circulation between them. But for a Hycean world, the global ocean fundamentally changes the calculation. Liquid water is an extraordinary heat distributor. Earth's oceans transport enormous quantities of thermal energy from equatorial regions toward the poles, moderating temperature extremes. A global ocean on K218b could similarly transport heat from the day side to the night side, potentially maintaining ocean temperatures across both hemispheres within ranges compatible with liquid water. Some atmospheric models of Hycean worlds suggest that even under tidal locking, the ocean atmosphere system could maintain habitable conditions across a substantial fraction of the planet's surface. Your quirky tidbit: the question of whether K218b is tidally locked cannot currently be answered directly by observation. We can measure that the planet orbits every 33 days. We cannot yet directly measure its rotation rate. Scientists infer the likelihood of tidal locking from theoretical models of how tidal forces evolve over the age of a stellar system, and those models suggest K218b is probably tidally locked but with significant uncertainty. There is a rare class of tidal states called spin-orbit resonances, where a planet doesn't fully lock but settles into an orbital rotational rhythm. Mercury, in our own solar system, rotates 3 times for every 2 orbits around the Sun rather than locking completely. K218b could occupy a similar state. We don't know. It's a detail that future observations may clarify. The radiation environment is perhaps the most genuinely threatening aspect of life around K218. Even if K218b's ocean maintains stable temperatures and the atmospheric chemistry is right, intense stellar flares could potentially strip away portions of the hydrogen atmosphere over millions of years and blast the upper ocean with radiation capable of destroying biological molecules. Life's response to this, on Earth, has been elegant in its indifference. Microorganisms that evolved in high radiation environments develop DNA repair mechanisms, radiation-absorbing pigments, and deep ocean refugia below the penetration depth of even the most energetic radiation. Evolution finds ways. It has done nothing but find ways for 4 billion years on this planet. Whether evolution has found ways on K218b is the question that everything else in tonight's story is circling. The star tries, the planet endures, And in the ocean below, if the DMS signal is real, something small and impossibly ancient is going about its business regardless. 120 light years. The number has appeared in this story many times by now, and each time it has probably felt like a big number, but perhaps not a viscerally enormous one. Numbers this large are difficult for human cognition. We evolved to estimate distances measured in footsteps and animal territories, not in light years. So let's spend some time making 120 light years real, because it is genuinely staggering, and staggering it properly is one of the most clarifying things this story can do for you. A light year is the distance light travels in 1 year. Light moves at approximately 299,792 kilometers per second. In 1 second, it travels from here to the moon and back with enough time left over to circle Earth 7 times. In 1 minute, it travels from Earth to the Sun. In 8 minutes, it crosses the entire Earth-Sun distance that keeps us warm and alive. In 1 year, light travels roughly 9.46 trillion kilometers. 1 year. 1 light year. 9.5 trillion kilometers. K218b is 120 of those. That is approximately 1.136 quadrillion kilometers from Earth. If you wrote that number out in full, it would be 1,136 billion. Let's try a few other scales to make this tangible. The fastest spacecraft humanity has ever launched is Voyager 1, currently the most distant human-made object, which has been travelling for over 40 years and is currently about 23 billion kilometres from Earth. At Voyager's speed, reaching K2-18b would take approximately 2 million years. Not 2,000, not 200,000, 2 million. At that pace, modern humans would have arrived not yet having evolved from our common ancestor with chimpanzees. The planet would be unrecognisable to anyone we sent, even if anyone could survive the trip, which they demonstrably could not. Your mainstream historical fact: the concept of the light year as a unit of distance was not always the standard in astronomy. For much of the 19th century, astronomers used the parsec as the primary unit of distance. A parsec being the distance at which one astronomical unit, the Earth-Sun distance, subtends 1 arcsecond of parallax angle, equivalent to about 3.26 light years. The parsec emerged from parallax measurement methods, the apparent shift in a nearby star's position against the background of more distant stars as Earth moves through its orbit, which were the primary technique for measuring stellar distances before the 20th century. James Webb data is reported in light years in popular science contexts, but professional astronomers more commonly work in parsecs and kiloparsecs. K218b sits at approximately 36.7 parsecs from Earth, for the technically inclined. What does the distance mean for any fantasy of contact or visitation? The answer is discouraging in a very clarifying way. Even if we sent a radio signal toward K218b today, a radio signal travelling at the speed of the light, which is by definition the fastest anything can travel through the universe under known physics, the signal would arrive in 120 years. A response, if sent immediately upon receipt, would reach us 240 years after we sent the original message. A conversation conducted at this speed would require the patience of geological epochs. Questions asked today would be answered in the 26th century. The entire span of recorded human history is shorter than the round-trip time of a radio exchange with K2-18b. and we have no means of travelling anywhere close to the speed of light. Our fastest spacecraft travel at roughly 1/10,000th the speed of light. At that speed, K218b is approximately 1.2 million years away. Plans for hypothetical future spacecraft, light sails pushed by laser arrays, nuclear pulse drives, theoretical antimatter engines, might conceivably achieve a fraction of a percent of light speed in the deep future. A 1,000-year journey to K218b might be theoretically possible, with technology centuries beyond what we currently possess, and a level of civilizational commitment that has never been sustained across generations on any project. Your quirky tidbit: the light you see from K218b, if you had a telescope powerful enough to observe it directly, left the star 120 years ago. You're looking into the past. You're seeing K218 as it was in 1905, when the Wright brothers had just flown for the first time, and nobody had split the atom yet, and the idea that a telescope would one day sniff the atmosphere of its planets would have sounded like the most extravagant science fiction. The light currently leaving K218b will arrive at Earth in 120 years. Whatever decisions we make today are being written into the signal Earth is sending outward right now, invisible and constant, washing past everything in its path. The distance doesn't make the detection less real or less remarkable. In fact, it makes it more so. Humanity has built an instrument so sensitive that it can analyze the atmospheric chemistry of a planet 1.136 quadrillion kilometers away and detect the possible presence of a specific biological molecule at the level of parts per billion in that atmosphere. Let that settle. Let the scale of that achievement sit beside the scale of the distance and compare them for a moment. The distance says we cannot go there. We cannot visit. We cannot send a probe in any time frame that a civilization surviving intact for that long would consider practical. We can only watch. We can only listen. We can only build better and better eyes and point them carefully at a dim red star in Leo and read what the light tells us. And what the light, 120 years old and tired from its journey, is telling us right now is among the most interesting things it has ever said. K218b did not become the most exciting planet in astronomy in a vacuum. It joins a list that has grown longer and more interesting with each passing year of exoplanet research, and whose members compete for telescope time, research funding, and the particular kind of anxious hopefulness that characterizes the astrobiology community on a good day. Understanding where K218b sits in the broader landscape of potentially life-bearing exoplanets gives you a sense of just how much the field has changed, and how rapidly the candidates for cosmic companionship have multiplied. The TRAPPIST-1 system remains perhaps the most discussed collection of exoplanets in the biosignature conversation. 7 Earth-sized planets orbit TRAPPIST-1, a red dwarf about 40 light-years from Earth, closer than K218b. 3 of those planets, designated TRAPPIST-1e, TRAPPIST-1f and TRAPPIST-1g, sit within the star's habitable zone and have received intense scrutiny from Hubble and now Webb. The appeal of the TRAPPIST-1 planets is their size. They're roughly Earth-sized and potentially rocky, making them more analogous to our own planet than a Hycean world like K218b. If they have atmospheres, and if those atmospheres contain the right chemistry, they would be among the most Earth-like habitats known. Webb observations of the inner TRAPPIST-1 planets in 2023 suggested that at least some of them may lack substantial atmospheres, a disappointing but scientifically informative result. the outer planets remain under investigation. Your mainstream historical fact, the TRAPPIST-1 system was discovered not by Kepler, but by a dedicated observing campaign using the TRAPPIST telescope, the Transiting Planets and Planetesimal Small Telescope, located at the La Silla Observatory in Chile. The initial discovery of 3 planets was announced in 2016, and 4 additional planets were confirmed in 2017, using a combination of ground-based and space-based observations, including Spitzer. The announcement of 7 Earth-sized planets around a single star, 3 of them potentially habitable, generated what may have been the largest single-day spike in public interest in exoplanet astronomy since the first exoplanet discovery around a Sun-like star in 1995. Researchers still debate the habitability prospects of individual TRAPPIST-1 planets, particularly regarding radiation environment and atmospheric retention under the flare activity of their red dwarf host. Proxima Centauri b deserves mention, the closest known exoplanet to Earth, orbiting Proxima Centauri, the nearest star to our solar system, at just 4.24 light-year away. A planet in the habitable zone of the nearest star is an extraordinary circumstance. Unfortunately, Proxima Centauri is an exceptionally active red dwarf, producing flares that would bombard Proxima b with radiation levels orders of magnitude higher than Earth receives from the Sun. Whether Proxima b has an atmosphere at all, let alone a habitable one, is genuinely unknown. No atmospheric detection has been made. Its closeness makes it tempting. Its radiation environment makes it concerning. The TESS mission, the Transiting Exoplanet Survey satellite, launched in 2018 as the successor to Kepler, has been cataloguing exoplanets across the entire sky and has identified numerous potentially habitable candidates. Among the more discussed are the planets in the TOI 700 system, where at least one Earth-sized planet in the habitable zone has been confirmed, and LHS 1140b, a rocky super-Earth in the habitable zone of a nearby red dwarf, which has an unusually favourable geometry for atmospheric characterisation and has been flagged as a high-priority target for Webb biosignature searches. Your quirky tidbit, the term habitable zone, has also been applied beyond planetary orbits. There is a galactic habitable zone concept, proposing that the Milky Way itself has a ring-shaped habitable region not too close to the galactic centre, where radiation and gravitational dynamics are intense, and not too far from it, where heavy elements necessary for rocky planets and complex chemistry are sparse. Our solar system sits in a relatively comfortable part of this galactic habitable zone. Some researchers argue this galactic geography, combined with the unusual stability of our Sun and our protective giant planet Jupiter, contributes to Earth's exceptional habitability in ways that the simple habitable zone definition understates. Critics call this rare Earth reasoning and argue it overstates how special our circumstances are. What distinguishes K218b from most of its competitors on this list is the combination of several factors arriving together: a habitable zone orbit, a confirmed substantial atmosphere, the detection of multiple organic molecules by Webb at high confidence, and the tentative detection of a biosignature candidate molecule. Other worlds on the list have one or two of these properties. K218b has all of them simultaneously. This is why, despite the caveats and the required scientific caution, it jumped to the top of nearly every astrobiologist's priority list after the Cambridge paper. The follow-up observation queue for K218b at the James Webb Space Telescope is substantial. More transits will be observed, more atmospheric data will be collected, the dataset will grow larger, the signal-to-noise ratio will improve, and the DMS signal will either strengthen and become more clearly attributable to biology, or it will weaken and perhaps be explained by alternative chemistry, or it will remain tantalizingly ambiguous and keep everyone in the field awake at night for another decade. All three outcomes are scientifically valuable. All three outcomes push the field forward. Meanwhile, a growing community of researchers is using K218b as a testbed for developing Hycean world atmospheric models, improving the theoretical framework so that future detections, whatever they show, can be interpreted with greater confidence. The planet is teaching us how to understand planets like itself. Even if the DMS turns out to be a ghost, K218b will have been worth every photon web spent on it. Science at the scale of James Webb does not happen in a vacuum, metaphorical or otherwise. The telescope exists because thousands of people wanted it to exist, argued for it persistently over decades, and because the institutions and governments funding it ultimately decided it was worth the extraordinary investment. Understanding how that decision got made, and what it cost, and what it displaced, tells you something important about the political economy of discovery, about how the most transformative scientific tools in history actually come to exist in a world where money is finite and priorities are always being contested. The James Webb Space Telescope was originally proposed in the late 1980s by a space science working group as the natural successor to Hubble, which was itself still being launched. Early estimates put its cost at roughly $500 million and its launch date around 2007. Both estimates were, in retrospect, charmingly optimistic, in the way that only the estimates of people who have never built a cryogenically cooled space telescope can be. By the time Webb launched on Christmas Day 2021, 14 years behind schedule, the total program cost had reached approximately $10 billion. It had become the most expensive scientific instrument in history. Your mainstream historical fact: in 2011, the United States House of Representatives voted to cancel the James Webb Space Telescope entirely, citing cost overruns and schedule delays in a subcommittee spending bill. The telescope was saved by an intense lobbying effort from the astronomical community, researchers, university departments, scientific societies, and individual scientists writing letters and testifying before Congress, as well as the intervention of senators from Maryland, where the primary contractor, Northrop Grumman, was headquartered. The episode illustrates both the vulnerability of a large-scale science to political budget cycles and the capacity of organized scientific advocacy to defend it. Historians of science use the JWST near cancellation as a case study in the politics of big science funding and the role of institutional lobbying in preserving long-horizon research investments. The allocation of Webb's observing time is itself a competitive and politically nuanced process. Scientists submit proposals, sometimes hundreds of pages of detailed scientific justification, to be reviewed by committees of peers who rank them against each other and allocate time accordingly. The system is designed to be merit-based. The most scientifically compelling proposals get the most time. In practice, the process involves implicit social dynamics of the kind that operate in any human institution, where experts evaluate each other's work. Reputation, institutional affiliation, the legibility of certain scientific styles over others, the career pressures that affect which projects get proposed in the first place. Every hour of Webb's time spent on K218b is an hour not spent on something else, and the scientists who didn't get time for their projects know this well. The international dimension is significant. Webb is a joint project of NASA, the European Space Agency, and the Canadian Space Agency. 3 space agencies with different national interests, funding structures, and scientific priorities. ESA built NIR-SPEC, one of the key instruments used in the K2-18b analysis. CSA built the Fine Guidance Sensor. Without international collaboration, the telescope would have cost even more and might not have survived its funding crises. The resulting science belongs to no single nation, which is, in the grand scheme of things, exactly appropriate for a tool built to answer questions that belong to the whole species. Your quirky tidbit: the James Webb Space Telescope's original budget estimate in the early 1990s was approximately $500 million in 1990s money. Adjusting for inflation, that would be roughly $1 billion in today's terms. The actual cost was 10 times that. This cost overrun pattern, called Hubbleitis in NASA circles after the similar pattern of escalating costs during Hubble's development, is not unique to Webb. Large scientific instruments almost universally cost more than initially estimated, partly because the technology required doesn't fully exist when the estimate is made, and partly because the estimation process tends to reflect the most optimistic, plausible scenario rather than a probabilistic center. This is not unique to science. It applies to most large infrastructure projects. But it is particularly consequential in science, where cost overruns can be used to argue against funding the next generation of instruments before the current one even flies. The funding of Webb displaced other projects. Science funding is a zero-sum game within any given budget cycle, and the money that went to Webb was money that did not go to smaller missions, university research grants, or other telescopes. The astrophysics community spent years negotiating internal priority lists, the decadal survey process, in which the community collectively ranks its priorities, trying to balance the extraordinary promise of flagship missions like Webb against the broader ecosystem of smaller, more nimble science. The current generation of astronomers has spent significant fractions of their careers in a funding environment shaped by Webb's existence, both in the opportunities it created and the trade-offs it required. None of this diminishes science. The K218b detection would not exist without the political will to fund Webb through 2 decades of difficulty, near cancellation, cost overruns, and technical setbacks. The discovery of a possible biosignature on a distant Hycean world is also, in a very direct sense, the result of senators from Maryland defending a budget line and scientists writing letters to congressional offices and international agencies agreeing to share costs and credit across borders. Science is done by humans. Humans operate in institutions. Institutions exist in political and economic contexts. The cosmic and the bureaucratic are always entangled. Imagine for a moment that the follow-up observations confirm it. Imagine that Webb observes another dozen transits of K218b, that independent teams analyse the data, that the DMS signal strengthens to 5 sigma certainty, that alternative abiotic explanations are ruled out one by one, and that a scientific consensus forms, quietly, carefully, through the normal processes of peer review and replication, that K218b's atmosphere contains dimethyl sulfide produced by living organisms in its ocean. Imagine that the announcement is made, not a press conference with a president's statement, not a Twitter leak, just a paper in a journal, with a title that understates everything about what it contains, as scientific papers always do. And the paper says, "We've detected evidence of biological activity on a planet in another star system." What happens next? The honest answer is that nobody knows with certainty. The event would be without precedent in recorded human history. Every civilization that has ever existed on Earth has done so in the working assumption, stated or unstated, theological or secular, that Earth is the only world containing life. Even civilizations that believed in the gods, in spirits, in the populated heavens of various religious traditions, believed that Earth's biological life was unique. The confirmation of extraterrestrial life would not be merely a scientific update. It would be a revision of the foundational operating assumption of human existence. Your mainstream historical fact: NASA commissioned a series of studies in the 1990s and 2000s to assess how the public might respond to the discovery of extraterrestrial life. These studies found, perhaps surprisingly, that the majority of survey respondents across multiple countries anticipated responding positively, with excitement, wonder, and a sense of expanded perspective rather than panic or religious crisis. However, social scientists have pointed out that self-reported reactions to hypothetical events are unreliable predictors of actual behavior, and that reactions would depend enormously on the nature of the life discovered. Microbial versus intelligent, close versus distant, passive versus apparently active. Researchers still debate whether modern societies are psychologically prepared for an announcement of this magnitude, and what institutional frameworks, scientific, governmental, religious, media, would need to be in place to manage the aftermath effectively. The religious implications would be complex and varied. Different faith traditions have in fact anticipated this possibility with more sophistication than popular culture typically credits. The Vatican Observatory has actively engaged with astrobiology. Vatican astronomer Guy Consolmano has written about how the discovery of extraterrestrial life would be compatible with Christian theology, arguing that a God who created life on Earth could certainly have created life elsewhere. Islamic scholars have engaged with the question in terms of verses in the Quran that refer to creatures in the heavens and the earth. Buddhist and Hindu frameworks, with their concepts of vast cosmic time and multiple worlds, may face fewer immediate theological challenges than Abrahamic traditions. The specific challenge would be greatest for traditions that assert a unique and central role for humanity in the cosmos, though even within those traditions, sophisticated theological responses are possible. The political implications would be immediate and unpredictable. The discovery would raise questions about whether K218b and its inhabitants, however humble, however microbial, deserve some form of legal or moral consideration. What rights, if any, do microorganisms on a distant ocean world hold? Can nations claim resources from that world? Does the confirmation of life elsewhere affect how we think about Earth's own biosphere and our obligations to protect it? International bodies would convene, treaties would be proposed, arguments would happen in languages the microbes in question cannot speak and would not understand. Your quirky tidbit, METI International, Messaging Extraterrestrial Intelligence, an organisation that advocates for intentionally transmitting messages toward potentially inhabited worlds, has already drafted preliminary frameworks for what a message toward a confirmed life-bearing exoplanet might contain. The existence of this organisational preparation tells you something about the degree to which serious people have been thinking carefully about exactly this scenario. Meanwhile, a parallel community of scientists argues that transmitting any message toward K218b before international consensus is reached would be a profound mistake, given that we know nothing about the nature or capabilities of the life there. The microbes are not the concern, but the principle of announcing our location and existence without global agreement is. The psychological impact on humanity at large would be gradual and then, perhaps, sudden. The scientific announcement would be followed by months of coverage, debate, and reanalysis. For some people, the discovery would produce a profound sense of connection, a feeling that life is a cosmic property rather than an earthly accident, that the universe is, in some meaningful sense, alive. For others, it might produce unease, the realization that we are not the universe's only project, that somewhere out there something exists with no awareness of us, no history we share, no reference point in common. The isolation of humanity would be simultaneously confirmed and broken. We'd know we weren't alone, but we'd also know the company is 120 light-years away, and fundamentally alien in every meaningful sense. And through all of this, in the ocean of K218b, nothing would change. The microbes would continue doing what microbes do: eating, dividing, dying, being eaten, producing DMSP, releasing DMS, exhaling into a hydrogen atmosphere under a red sun. They would be, in the deepest sense, indifferent to their own discovery. They would not know we exist. They may never know. The relationship would be profoundly one-sided. We who have been changed forever by them, and they who remain unchanged and unaware. There is something very humbling about that. The question of whether to try to contact K218b is one that sounds, on first hearing, almost comically premature. The possible inhabitants are microbes, ocean microbes, single-celled organisms that, as far as any evidence suggests, produce dimethyl sulfide and have no discernible opinions about interstellar communication. You don't send a message to plankton, even very enthusiastic plankton. The physics of any response would take 240 years just for a round trip at the speed of light, and the biology of the recipient suggests the message would need to be formatted in a way that ocean microbes could interpret, which is a design challenge that would challenge even the most adventurous communication theorist. But the K218b discovery, if confirmed, would not exist in isolation. It would be the first known inhabited world beyond Earth, and the discovery of the first would inevitably prompt questions about others. About whether any of those others host intelligent life, about whether any of those others is already listening, and about what humanity should do with the knowledge that it now possesses. That life exists in the universe, that the universe is biologically populated, and that we are either alone among the thinking things, or we are not. And if we are not, whether we should announce ourselves. SETI, the search for extraterrestrial intelligence, has been listening for signals from the universe for more than 60 years. METI, Messaging Extraterrestrial Intelligence, is its more controversial counterpart, the project of sending messages outward. The debate between these two activities is not merely tactical. it touches on one of the most important and least resolved questions in the philosophy of interstellar relations. Is it safe to announce ourselves to the universe? Your mainstream historical fact. In 1974, Frank Drake and Carl Sagan composed and transmitted the Arecibo message, a binary encoded signal broadcast toward the globular cluster M13, containing a pictorial representation of DNA, a human figure, our solar system, and the Arecibo telescope itself. The message was sent at 2,380 MHz for 3 minutes during the rededication of the Arecibo telescope in Puerto Rico. It was, by design, almost certainly not going to be received by anyone for at least 25,000 years. M13 is 25,000 light-years away, and the transmission was widely understood as symbolic, a demonstration of capability rather than a serious first contact attempt. Scientists still debate whether the Arecibo message was a wise precedent, a harmless gesture, or the kind of thing that, had it been directed at a closer and more responsive target, might have been a decision worth making collectively rather than unilaterally. The argument against METI, the argument for what its opponents call cosmic caution, has been made forcefully by several prominent scientists, most famously Stephen Hawking, who repeatedly warned in interviews and lectures that contact with an advanced civilization could be catastrophic for humanity. His reasoning was straightforward. The history of contact between technologically unequal civilizations on Earth is not a comforting guide. When European civilization encountered the civilizations of the Americas, Africa, and much of Asia, with significant technological advantages, the outcomes for less technologically advanced societies were generally catastrophic. Not always through malice. Disease, economic disruption, and cultural destruction were often as damaging as deliberate violence. An intelligence capable of crossing or communicating across interstellar distances would, almost by definition, be technologically our superior. Hawking thought announcing ourselves to such an intelligence was unwise. The counter-argument made by SETI researchers and METI advocates is that any civilization capable of reaching or affecting Earth from another star system would already know we're here. Earth has been leaking radio transmissions into space for over a century. The electromagnetic bubble of our civilization, the expanding sphere of radio waves from television, military radar and broadcast signals, is now over 100 light-years in radius. We are not hiding. The horse, in this argument, has left the barn, and a locked barn door after the fact is both too late and philosophically inconsistent. Your quirky tidbit, the most famous unintentional message humanity has sent into space, is probably not a radio signal, but a physical object. The 2 Voyager spacecraft launched in 1977 each carry a golden record, a gold-plated copper disc containing sounds, greetings in 55 languages, music from multiple cultures, and encoded images representing Earth and its inhabitants. The records were designed by a committee that included Carl Sagan and Andrewian, and they were intended for any intelligence that might ever encounter the spacecraft. The Voyagers will travel through interstellar space essentially forever, or until something intercepts them. They are currently the most distant human-made objects, and the only physical artifacts humanity has dispatched beyond our solar system. Whether anything will ever find them is a question about the density of interstellar space and the prevalence of spacefaring civilizations. 2 numbers we do not know. The specific case of K218b adds a new dimension to the METI debate. If the life there is confirmed as microbial, the immediate communication question dissolves. You don't send radio signals to plankton. But K218b's confirmation would be evidence that life is not rare, and that evidence raises the probability that intelligent life exists somewhere in the galaxy. The question of whether to announce ourselves to whatever else might be out there becomes more pressing, not less. Once we know the galaxy is biologically populated, and it becomes a question with genuine stakes, which means it is a question that deserves global deliberation rather than the decision of any single institution, agency, or enthusiastic individual with access to a large antenna. The microbes of K218b, if they exist, will never hear from us. But the question they raise may be the one that determines how humanity chooses to introduce itself to the rest of the universe. After the September 2023 paper, the scientific community did not rest. Science doesn't rest after a preliminary detection. It leans forward, schedules more observation time, argues about methodology, and starts designing the follow-up work that will either solidify a discovery into history or dissolve it back into the noise it came from. The K218b story is actively unfolding right now, not in the sense of waiting for something to happen, but in the sense that telescopes are pointed at this system, data is being collected, papers are being written, and the answer is getting incrementally less uncertain with every observation. The most important next step is additional Webb transit observations. The original Cambridge paper was based on a limited set of transits, enough to make a preliminary assessment, not enough to produce a definitive molecular inventory. Astronomers have secured additional Webb time to observe more transits of K2-18b, building up the spectral signal with each observation. As the dataset grows, the signal-to-noise ratio for each molecular detection improves. The DMS signal, if it is real, will become clearer and more statistically robust. If it was a noise artifact or a modelling error, it will fade as better data constrains the atmospheric composition more tightly. Your mainstream historical fact, the process of following up on potentially significant exoplanet atmospheric detections, has a precedent in the 2020 announcement that researchers had detected phosphine in the atmosphere of Venus. Phosphine, pH3, was reported using observations from the JCMT and ALMA telescopes, and the detection attracted enormous attention because phosphine in Venus's atmosphere lacked a known abiotic source and was tentatively suggested as a possible biosignature. Subsequent reanalysis by multiple independent teams revealed significant problems with the original data reduction, calibration errors, and misidentification of spectral features that had amplified the apparent signal. By 2021, the scientific consensus had largely moved toward viewing the original phosphine detection as an artifact of data processing. The episode is now used as a cautionary tale about the importance of rigorous independent verification for biosignature claims, and researchers studying K218b are well aware of it. Scientists still debate whether any residual phosphine signal in Venus's atmosphere exists at a lower level than originally claimed, with some groups arguing a genuine but smaller signal may be present. The second major observational avenue is direct imaging and high-resolution spectroscopy of K218b when it is not transiting, the day-side or night-side phase of its orbit. As the planet orbits, the angle at which we observe it changes, and advanced techniques including secondary eclipse spectroscopy, measuring the drop in light when the planet passes behind its star, can provide additional constraints on the atmospheric composition from the day side. This approach is technically challenging for a planet as small and cool as K218b at this distance, but Webb's capabilities are being pushed to their limits in pursuit of exactly this kind of detailed atmospheric mapping. Independent teams are also reanalyzing the existing Webb data using different atmospheric retrieval codes and different underlying molecular databases. This kind of parallel independent analysis is a cornerstone of reproducible science. If different teams using different methodological choices arrive at similar molecular identifications, confidence increases substantially. If they arrive at different conclusions, the discrepancy itself is scientifically informative. It reveals where the modelling uncertainties are largest and where additional observational constraints are most needed. Laboratory measurements are a third critical thread. Several research groups are conducting new experiments to measure the precise infrared absorption spectra of dimethyl, sulfide and related sulfur compounds under conditions mimicking a Hycean atmosphere. High hydrogen content, low temperature, specific pressure ranges. Current molecular databases were primarily compiled for Earth-like or hot Jupiter conditions. Better laboratory data for Hycean-relevant conditions will sharpen the atmospheric retrieval models used to interpret Webb spectra and reduce the ambiguity in the K2-18 BDMS identification. Your quirky tidbit: the laboratory measurement of molecular spectral features for astronomical databases involves cooling gas samples to extremely low temperatures, sometimes just a few degrees above absolute zero, and passing infrared light through them to measure exactly which wavelengths are absorbed at the conditions found in planetary atmospheres. This sounds straightforward until you realise how many molecules matter for planetary atmospheres, thousands of them, and that each molecule has a spectral fingerprint that varies with temperature and pressure in complex ways. The researchers doing this work are, in a very real sense, building the dictionary that lets Webb read alien atmospheres. Without accurate molecular databases, even the world's greatest telescope is shouting into a room without knowing what words mean. The timeline for definitive resolution of the K218 BDMS question is uncertain. Some scientists are optimistic that additional Webb observations over the next few years, perhaps by the late 2020s, could push the DMS detection to 5 sigma confidence or convincingly rule it out. Others caution that the inherent limitations of transmission spectroscopy for a molecule present at trace levels, combined with the modelling uncertainties of Hycean atmospheres, might mean that Webb alone cannot settle the question definitively. Longer term, the next generation of extremely large telescopes, ground-based instruments with mirrors 30 to 40 meters across, including the extremely large telescope currently under construction in Chile and the 30-meter telescope planned for Hawaii, will have atmospheric characterization capabilities that complement Webb's space-based measurements. Combined with potential future space telescopes specifically designed for biosignature searches, the scientific infrastructure for answering questions like K218b's is being built now, piece by piece, with K218b as the motivating example. The answer is coming, slowly, carefully, as all real answers do, and whatever it turns out to be, the act of asking it, with golden mirrors in space and patient scientists staring at spectra in Cambridge, and chemical databases compiled by people who cared enough to freeze molecules to the edge of absolute zero and shine light through them, is, all by itself, one of the most extraordinary things our species has ever done. Here is the thing about tonight's story that is easy to miss when you're moving through the technical details, the spectroscopy and the sigma levels, and the Hycean world models, and the photochemical alternatives. The thing that sits quietly underneath all of it and doesn't announce itself, but is perhaps the most important fact of everything you've encountered tonight. You're alive right now. You, specifically, in this specific era. And that is, in the context of the 4 billion year history of life on Earth, a fact of almost impossible timing. Life has existed on this planet for roughly 4 billion years. For most of that time, the most complex organisms were single-celled. For most of the remaining time, no organism had the cognitive architecture to ask questions about the universe. For virtually all of recorded human history, the question, "Are we alone?" was unanswerable by any means. Not just unanswered, but structurally, physically unanswerable, because the instruments that could answer it did not exist. You are alive in the first era in the history of life on Earth, during which that question is becoming answerable. Not answered, not settled, but answerable. The tools exist, they're in operation, they're pointing at the right places, and the data they're returning is, for the first time, biologically interesting in ways that previous data was not. Your mainstream historical fact, the James Webb Space Telescope, is the culmination of a particular tradition in science, the systematic magnification of human perception through engineered instruments. The first telescopes, made by Dutch lens grinders around 1608 and quickly turned to the sky by Galileo in 1609, extended human vision to reveal moons around Jupiter and phases of Venus. Subsequent centuries brought ever larger and more precise instruments, each revealing a universe larger and stranger than the previous generation had known. Webb is the latest step in this 400-year tradition of looking harder. It represents, in the most literal sense possible, the furthest extension of human curiosity into the structure of the universe that our civilization has yet achieved. Historians of science will mark this era, the early decades of Webb's operation, as the period when exoplanet atmospheric characterization moved from aspiration to practice. Spend a moment with the human side of this. Niku Madhusudan, who led the K2-18b team, grew up in India, studied mathematics and physics, became an astrophysicist, went to Cambridge, and spent years developing the theoretical framework for Hycean worlds before Webb gave him the data to test it against. The engineers who built NISPEC went home at night to their families, their ordinary evenings, their unremarkable dinners, while the thing they had built sat in space collecting light from another world. The scientists who stayed up late reanalyzing the data, the peer reviewers who scrutinized the methodology, the editorial team at the Astrophysical Journal letters who processed the submission, all of them ordinary people doing specific tasks that contributed, in aggregate, to a data set that may contain the first evidence of extraterrestrial life. Science is not a single eureka moment. It is 10,000 quiet acts of attention, done carefully and honestly over decades, by people who mostly go unremembered. The discovery, if K218b's DMS holds up, will be remembered. The people who polished the mirror segments and measured the molecular absorption features and wrote the retrieval code will not be, by most people, by most of history. And yet without every one of them, the photons from K2-18b would have arrived at Earth and passed through and kept going forever, unread. Your quirky tidbit: the letter B in K2-18b indicates that it was the first planet discovered in the K2-18 system. If a second planet is ever confirmed, it would be K2-18c. There is in fact a candidate signal in the K2-18 data that some researchers believe may indicate a second planet, though it is not confirmed. The naming convention is so understated it borders on the endearing. A world that may contain ocean life, that may be the most important object in the human sky, designated by a letter so small it barely registers. You have spent this entire journey, from the Cambridge office in the autumn of 2023 to the golden mirror in space, to the Hycean ocean under a red sun, to the equations of Drake and the silence of Fermi and the smell of the beach that is also a potential signature of alien life, arriving here. At this thought, the universe is very old and very large, and has been, for most of its existence, apparently silent on the question of whether it contains company for Earth. And now, for the first time in 4 billion years of Earth life, and 200,000 years of human life, and 400 years of telescopic science, and 60 years of formal extraterrestrial life searches, the silence is cracking slightly. A molecular signal from a dark ocean 120 light-years away is saying, very quietly in the language of chemistry, maybe here, maybe not alone. The answer's not yet final, the work continues, but you, the specific person in this specific time, are alive while it is happening. You get to know the question and watch the answer come. That is not a small thing. And now, let these thoughts begin to soften. Let the momentum of the story ease. You have travelled, in the last hour or so, from Cambridge to L2 orbit, to a Hycean ocean, to the silence of Fermi, to the political halls where science is funded, to the philosophical aftermath of a discovery not yet made. That is a long way to travel in one evening. It's all right to let it drift now. The star K2-18 is burning right now, in the direction of Leo, 120 light-years away. Its light is crossing that distance at 299,792 kilometers per second, carrying the fingerprints of a world in its wavelengths. That light will arrive here in whatever fraction of 120 years remains, and Webb, or something that comes after Webb, will read it. The reading will continue, patient and precise, for as long as the instruments hold and the funding continues and the humans who tend them keep showing up. And K2-18b is there, orbiting as it has been for billions of years, every 33 days around its dim red star. The ocean, if it exists, is rolling slowly in whatever currents its tidal forces and atmospheric dynamics generate. The hydrogen atmosphere is pressing down on the water's surface, and in the upper ocean, in that twilight zone where just enough dim red light penetrates and just enough chemical energy is available, something small may be alive. Something that has never heard of Earth, has no concept of a telescope, has no awareness of having been noticed. Something that breathes out a molecule that smells of the sea. Let that image carry you now. Not the complexity of the science, not the uncertainty of the detection, not the enormity of the implications, just the image. A dark ocean, 120 light-years away, under a reddish sky, somewhere in the direction of Leo, quiet, old, breathing. The universe is very large and you're very small, and tonight you lay in the dark and thought about something that might be living in an ocean you will never see, and that act, that reaching of the mind across an impossible distance, is perhaps the most distinctly human thing there is. Curiosity aimed outward, into the night. Let your breathing slow. Let your thoughts become less precise and more like impressions. The colour of a red star, the smell of the sea, a graph with a small peak that might mean everything. Let the story settle into the part of you that holds things like wonder, the part that is quieter and older than language. Webb is still out there, still watching, still collecting photons from 100,000 worlds. The work doesn't stop when you sleep. It continues steadily in the cold and the dark, with patience that belongs to something built rather than born, waiting for the next transit, the next spectrum, the next answer. Sleep now. The universe will still be there in the morning, and tomorrow it might be just slightly better understood.